Hello! In this video, I'm going to derive equation related to escape velocity, velocity of satellite, and period of rotation of the satellite. Then we're going to discuss and do question related to these three subtopics. Okay, let's start with escape velocity, where the definition is the minimum initial speed that required so that object can move upward forever, okay, from the surface of a planet. So we draw, so we have a planet, okay, so we want to calculate the escape velocity for the planet, for the object to move forever from the surface of the planet, okay. So it will be from the surface of the planet to infinity. So how to derive? We're going to apply the first conservation of energy, where E initial equal to E final. So we have Ki plus Ui equal to K final plus U final. Okay, so substitute all the equation for kinetic energy and gravitational potential energy. Okay, then we need to assume at r equal to infinity, our v will equal to 0 meter per second. So therefore, from this information, we will get 0 for the final energy. Okay? Since our E final equal to 0, so we can rearrange our equation. So we get V escape to be square root 2 gm divided by r, where r equal to radius of the planet, m is the mass of the planet, and g is gravitational constant, that is 6.67 exponent negative 11. Okay, next we move to velocity of satellite. So how can we derive the velocity of satellite? Okay, so first we need to consider a satellite of mass m traveling, okay, in a circular path around the planet with a constant speed v. Okay, so big M will refer to mass of planet and r will refer to the radius of circular orbit. So we need to use our centripetal force to derive this equation. Okay, so first I sketch first the situation. Okay, so we have a satellite that orbiting around the planet. Okay, so this satellite will experience gravitational force and also centripetal force both towards the center of the planet. Okay, so we can let Fg to be equal to Fc. So substitute both of the equation. Okay, so we can cancel satellite and radius of the circular orbit. Then we will get the final equation for velocity of satellite to be v equal to square root gm divided by r. Okay, where r is the distance from the center of planet to the object and m is the mass of the planet. Okay, so r is referred to radius of the earth plus with altitude, that is expressed as h. Okay, let's look at the last equation that we're going to derive, that is period of rotation. It is a time taken for satellite to complete one revolution around the planet. So from circular motion, we know that v equal to r omega and omega equal to 2 pi divided by t, that is period. Okay, thus v equal to 2 pi times r divided by t. Okay, so substitute v equal to square root gm divided by r into equation 2. Okay, so we have 2 pi divided by t equal to square root gm divided by r. Rearrange the equation, then we get t equal to 2 pi square root r cubed divided by gm. Okay, let's try the first question, PSPM 2011-2012. Okay, so sketch your understanding based on the question first. 1000 kg satellite is in an orbit 350 km above the Earth surface. Okay, so we have the mass, we have our big M, that is the mass of the Earth, and we have our R, that is the distance from the center of the Earth to our satellite. Okay, given that the radius of the Earth to be 6.63 exponent 6 meter. Okay, so we use the equation for velocity to calculate the speed of satellite. So square root gm divided by r. Substitute all the information given. So we get the speed of the satellite to be 7.70 exponent 3 meter per second. Next, to calculate the period of the satellite, we're going to use t equal to 2 pi square root r cubed divided by gm. Okay, so substitute all the information given into the equation. Okay, then we will get an answer for the period to be 5.51 exponent 3 second. Okay, and for the radial acceleration of the satellite, okay, radial acceleration refer to centripetal acceleration. So v squared divided by r. So we already have our v. Substitute into the equation, and r is the distance from the center to the satellite. So we get 8.78 meter per second square. Okay, next question is PXPM 2013-2014, where we have a mass and radius of the Earth to be 5.974 exponent 24 kg and 6371 km for the radius of the Earth. So it asks to calculate the period of revolution of satellite that is 100 km above the Earth's surface. Okay, so we have altitude, we have our radius of the Earth, so we can find the distance from the center to the satellite. So we use the equation for period, substitute all the information given into the equation. Okay, then we will get answer to be 5181 second. Okay, so for the radius, make sure you put cube. Okay, I forget to write the cube. Okay, next question is more question from one of the matriculation school or matriculation college in Malaysia. Okay, so we have International Space Station, okay, launched from the Earth and orbiting at an altitude of 350 km. So it has a mass of Earth. It gives you the radius of the Earth. So it asks you to find the velocity in order to escape completely from the Earth gravitational pull. So we're going to use the escape velocity equation. Okay, substitute all the information given. Okay, for escape velocity, r refer to the radius of the planet itself, that is the radius of the Earth. Okay, so once you substitute all the information given, you will get the answer to be 7906.84 meter per second. Okay, next question. Given the ISS has a weight of 4.22 exponent 6 Newton when it is measured on the surface of the Earth. Okay, calculate the weight of the ISS when in its orbit. Okay, so we know that our gravitational acceleration or gravitational field strength will vary based on the distance from the center of the Earth. Okay, so two equations that we're going to use to solve this problem, that is weight equal to mg and g equal to gm divided by r squared, where r is the distance from the center of the Earth. Okay, so at surface we have weight 4.22 exponent 6 equal to mass of the ISS. Okay, and gm, okay, gravitational constant, times with the mass of the planet, okay, divide with the radius of the Earth, and at its orbit, okay, so we have we put W represent the weight of the ISS when it is in the orbit, and we have our small m refer to the satellite, the mass of satellite. Okay, and we have our r value to be 6.63 exponent 6 plus with 350 exponent 3. Okay, 350 exponent 3 is the altitude. Okay, then we can compare equation 1 and equation 2. Okay, once we compare the equation 1 and equation 2, okay, substitute all the information given. Okay, so we get the weight of IS to be 3.81 exponent 6 Newton. Okay, so for the last one, let's find the velocity and period of revolution of the IAS in its orbit. Okay, so we have V equal to square root gm divided by r. Substitute all the information given into the equation. Okay, then we get the value for velocity of IAS to be 7.69 and exponent 3 meter per second. Okay, for the period, it is t equal to 2 pi square root r cube divided by gm. Okay, so substitute all the information. Sorry, I forget to put the cube. Okay, make sure you put cube, so your final answer will be 5492.74 second. Okay, so that's all for this video. I hope you enjoy. Okay, so please subscribe and like my video. Thank you.